Alrighty, let's talk about how phosphates react now. Phosphates have two mechanisms that you're responsible for knowing. One kind of follows all the trends that we've taught you up until this point when we went through the carboxylic acid derivatives chapter, and the other one's a little less obvious, but we'll save that for last. So for the mechanism that would be most obvious to what we have learned so far in this course, it's, well, we see P double bond O, we can think of that the same way as we thought of C double bond O. Things like to attack that carbon and swing those electrons up. And such is the case here. That O minus can come in, attack the phosphorus, and resonate those electrons up. And now I've labeled this oxygen O18 just so we can keep track of where it ends up in the final products between our two mechanisms. So what's going to happen is this attacks the phosphorus, that resonates up, and we get our first intermediate. We would have phosphorus, single bond O minus. We'd have the OH that attached, and that should be my red labeled O18. O18. And then we have the three OR groups that were there formerly. O ethyl, O ethyl, O ethyl. And then, just like in our carboxylic acid derivatives chapter, what's going to happen next is that O minus is going to resonate down and kick out a leaving group, and in this case it's going to be one of the three OR groups. Doesn't really matter which, they're all the same. Let's just say it's the one on the right. And so as a result, we'll get now double bond O, phosphorus, the two OR groups that remain, plus the O18 that we just added. Now there's one last step we have to do. We're almost at the final product. Because we have just made this, and we're in a solution of OH minus, a very good base. Now, that OH minus is always capable of pulling off protons or attacking carbonyls. But in this case, the first thing that's going to happen is pull off a proton. Because why would this choose to pull off a proton rather than attack a carbonyl, or be double bond O in this case? Well, think about it this way. What we have right now is very similar to a carboxylic acid, a carbonyl with an OH. And we learned that these hydrogens are very, very, very acidic. The same is true here. This hydrogen is very readily able to pop off. And one thing we will stress over and over again is acid-base reactions are the fastest things to happen. Yes, you could attack the carbonyl, but it would happen at a much slower and less common rate than just pulling off that proton, because all you have to move is a hydrogen, a very easy thing to break or move around. Whereas if it were to attack the phosphorus, well, you'd have to finagle the oxygen into the phosphorus around all these groups that could potentially repel it with their own electrons, and then we have to worry about the resonance and all the other stuff. Whereas all we have to do with this is a simple hydrogen just whoop, right off. So what's going to happen is this will get deprotonated by the base that's floating around. So I'll draw it this way. So we have some OH minus floating around still, and technically it's the O18, but I'm only caring about the one that ends up on the phosphorus. This comes in, grabs your proton, the electrons from the bond swing onto the O minus, the O18, and you get an O minus. So what you're left with in your final product is carbonyl, phosphorus, O18 minus. And then the other two OR groups. Now, why can't that OH come in a second time now that there's no acidic proton? Why wouldn't it just want to attack the phosphorus now? Well, it's because it will try, but it will fail. That O minus will try and come in and attack, but think of it this way. We have another O minus right here. There are the electrons of that O minus floating around, repelling this O minus away. So, long story short is, when you have something O minus attacking a phosphorus group like this, you only add something once and kick out a leaving group once. They're not going to keep adding over and over again. Alright? And really that's it. All you have to know is your basic reaction right here, and it's nothing really different from what we learned from the carboxylic acid derivatives chapter. So now comes the other mechanism you're responsible for, which is a little less obvious. We're going to start with the same exact materials, get the same, and we're going to see the other way it can react. So let's see. Once again, we're going to follow that O18 minus. Now, if it's not attacking the phosphorus here and resonating the oxygen up, where else does it have an option of attacking? Well, this is what makes phosphates react a little differently from what we're used to. What this oxygen can do is, rather than attacking the phosphorus this time, it can attack the carbon of your OR group. And when I say the carbon, I mean the carbon that is a single bond away from the oxygen of that OR group where it's connected to the phosphorus. So right here, here, or here. Since these are all equivalent, it doesn't really matter which one I choose. So I'm going to say this one. Okay, and so this will pop off and put the electrons onto that oxygen. And so what you'll get is essentially the same answer we got before, but the difference is where that O18 is at the end. The two other OFLs are completely unchanged. And where is that O18? It's attached to the carbon that lost its bond to the oxygen, meaning we have the HO18 and then these two carbons on it as well, CH2, CH3. So these would be the two products from this mechanism. So how do you know when you're going to use one mechanism over the other? You really can't. And the way we'll tell you in an exam question is probably by giving you the products that we expect. We'll label the oxygen in the product and say, okay, so we should see that the oxygen is either attached to the phosphorus, in which case you'll use the first mechanism, or you'll see the oxygen that we labeled is in a separate group altogether, in which case you're going to follow this mechanism. Now let's modify this concept, this mechanism I mean, and just ask a very similar question on which would be the better OR group. So what I'm going to do is I'm going to just slightly change what these OR groups look like. I'm going to add a methyl to this carbon, a methyl to this carbon. Actually, no, I'm going to keep that there. I'm going to put the methyl on this carbon, just so it's easier to draw for me. Okay, so what I've done is I've made it from just a straight carbon ethyl chain to a, what's it called, a isopropyl group. In other words, it's just two carbons off instead of a single chain. Now, again, that O- can come in and attack, but where is it going to attack this time? In the previous example, there was no difference between the OR groups, so how do I know where this one's going to preferentially attack? The way it works is this most likely follows essentially an SN2 styled mechanism of sorts, meaning the fewer groups you have where that oxygen attacks, the better it is for the reaction to occur. Meaning, if I look at this carbon right here, it's a secondary carbon. It has two methyls on it. Same deal with this. That's a secondary carbon, and that means when this O- tries to come in, it's going to have a harder time fitting into that spot. Whereas if it comes in and attacks here, there's no issue of steric hindrance quite like these two have. It's just hydrogens there that are in the way, and then that one carbon. This is primary versus two secondaries. And if I were to add another methyl onto this one, and I were to say, okay, of these three OR groups, who's going to be the most reactive or the best to react in this manner? Well, like we said before, the more steric hindrance or the more methyls you have, the less reactive it's going to become because it's going to be harder for that oxygen to fit in and follow this mechanism we're drawing out. So in this case, the OH would be much more readily able to attack here, a little less readily able to attack here, and almost impossible to attack here because it's so sterically hindered. So if they show you an example like this on the exam, you just need to know that if we're assuming that we're trying to attack the carbon instead of the phosphorus, so we're using mechanism 2, you're going to favor attacking the less substituted carbon. Okay? And so if that were the case, the product you would get would be this plus the other two unchanged. So the isopropyl and the tert-butyl would be like that. Okay? And really that's it for mechanisms. And I don't even know if they'll go so far as to ask you this concept. It's something I really just mulled over in my head and figured why not explain it, because it's old Orgo 1 nonsense that could be applicable somewhere else on your exam. But with that said, that's all you need to know about phosphates. There's really not that much about it. You know your names, you know your mechanisms, and you know your pKa versus pH rules, and you're fine. There shouldn't be much they can do beyond that.